Hello everyone. In this MATLAB and control systems tutorial, we explain how to define transfer functions and how to define responses of transfer functions to user-defined input signals. That is, we explain how to compute the responses of transfer function to arbitrary input signals. First of all, let's explain how to define transfer functions in MATLAB. Let us consider a second-order transfer function in the general form given by this equation. In the numerator, we have a polynomial that looks like this: a2 multiplying s squared plus a1 multiplying s plus a0. Similarly, in the denominator, we have a polynomial that looks like this: b2 multiplying s squared plus b1 multiplying s plus b0. Over here, a2, a1, a0, b2, b1, and b0 are the coefficients of the polynomial, and s is the complex Laplace variable. To define this transfer function in MATLAB, we need to define two vectors or two arrays storing the coefficients of the polynomials in the numerator and the denominator. The array storing the coefficients of the polynomial in the numerator is a2, a1, a0, and similarly the array or the vector storing the coefficients of the polynomial in the denominator is equal to b2, b1, and b0. Once we define these two arrays, we can simply define the transfer function as follows: tf of num, den. And this function will return a transfer function object. Now let's define a transfer function with exact numerical values. W will be equal to 2s squared plus 0.5s plus 0.4. In the denominator, I will have 0.5 s squared plus 0.1 s plus 0.3. Let's define this transfer function in MATLAB. The first step is to define the array storing the coefficients of the polynomial in the numerator. This array is 2, 0.5, 0.4. Then we need to define array storing the coefficients of the polynomial in the denominator. This array is 0.5, 0.1, 0.3. Next, we define a transfer function as follows: w is equal to tf of num, den. And this function will return a transfer function object. Here it is. Let's make sure that everything is correct. 2, 2, 0.5, 0.5, 0.4, 0.4, and you can see that the coefficients in the denominator are also correctly defined. Okay, our goal is to compute the response of this transfer function to a user-defined input signal. Let's do that. To define an input signal, we first need to define the simulation time. I will call the simulation time as time s. Time s will start from 0 with the step of 0.01 and it will end at 10 seconds, or let's say 15 seconds. Then we need to define a control input. Over here, I will define a control input u that has this form: 2 multiplying sine 3t plus 1 multiplying cosine of 4t. I'm using this function, however, you can also define an arbitrary function. So let's define this function. Okay, I will call input u, and the input u will be 2 multiplying sine 3 multiplying time s plus 1 multiplying cosine of 4 multiplying time s. Okay, that's our input and output. Let's plot this input and output. We can simply do that by defining a figure, and we can specify the time vector, time s, and then we can specify the input vector, input u. And let's see it over here. Here it is. Here is our input. Looks good. Okay. To simulate the response of our transfer function to this input, we need to use the function lsim. The first input argument of lsim is our transfer function. The second input argument is our input u. The third input argument is actually the simulation time. And that's it. So let's simulate our system. However, before lsim, we will specify the figure, since I don't want to overlap the graph on figure 1. And let's see the response. Okay, so here's figure 2. Let me now erase this such that we can analyze this figure. This graph shows the input, and this graph shows the output as well as the input. Let's insert the legend such that we can better distinguish the graphs. You can see that the blue line, that is this line, represents the simulated output. And you can also confirm that by clicking over here. You can see system, you can see the current time, and you can see the amplitude. Now, what is this gray graph? If you click on the gray graph, you'll see that this is actually the input that's also shown over here. Okay, now we know how to simulate a response to a transfer function to an arbitrary control input. But before I conclude this video, let me explain you one additional thing. Now, often you would like to extract the values of the simulated output. Let's learn how to do that. To do that, we can simply write, I will call the output as ys, the simulated time will be ts, and again you need to call lsim, w, input u, and time s. Okay, now over here I will generate another figure. I will call it figure 3, and in this figure 3 I will plot the extracted response so we can compare it with the graph generated by MATLAB. Okay, so that's it. Simple as that. And so let's see the result. And here it is. This figure shows the plot of the response on the basis of the extracted data, and this is automatically generated graph by MATLAB, and you can see that they perfectly match together. And finally, let's explain one important thing. Over here, it's implicitly assumed that the initial condition for simulation is actually 0. However, often you would like to simulate the response of your system for a specified initial condition. So let's explain how to do that. Over here, I will specify my initial condition. Since my original system is a second-order system, I need to specify two initial conditions. The first initial condition will be 2, and the second initial condition will be 1. And then again, we need to use this function lsim, input u time s. However, as the last argument, we need to specify the initial condition. And over here, I will call the graph figure 4. And finally, let's simulate this and let's see the output. And here's the figure 4. Now, let's compare figure 2 and figure 4. Figure 2 is the response of the system to 0 initial condition, and this figure is the response to non-zero initial condition. Okay, they are almost identical. So probably they are not. However, because you can see the scale here is relatively large, we cannot see any difference. To see a difference, we actually need to change the initial condition to make the response to be more dramatic. What if I put 20 here as the initial condition? And let's now repeat everything and let's see the response. Okay,